Okay, ladies and gentlemen, welcome back to part 3, where we look at the EM spectrum. Now, page 638 of your text talks about this nicely. I'm just hitting the high points. Now, we go here to the pink sheet. We look at radio or low frequency. So first thing, radio or low frequency. Now, these are something like 100 sorry, had a brain fart there. 100 megameters or 100 million meters in wavelength. Now, these can be produced by household appliances. So, some of you guys, you turn on the vacuum cleaner, the cordless phone goes weird. Cordless phones and radios. Oh, I want to point out there's no hard and fast definition regarding wavelengths. So, if you look at the pink sheet, they're going radio waves, 100,000 meters long buildings. You go to the green sheet, they're talking radio waves. You get long radio waves, you get short radio waves, AM, TV. It depends on who you're talking to. So, I'm going to stick to about 100 megameters. Now, the second one I want to talk about, AM, FM, this would be TV, radar stuff. These go from about 100 kilometers long to about 10 meters long. These are easy to create. If you got a cell phone, you're making them right now. Technical term is electric oscillating circuits. Oscillator circuits, sorry. You've got electrons oscillating and moving back and forth, creating these waves, AM, FM, TV, radio. So we're somewhere on the green sheet, radio-ish, depending on how you look at this. The green sheet talks about long radio waves, radio AM, FM radio waves. They're splitting it up. I'm not, no, well I am, but into low frequency and AM, FM. So once again, there's no standard set cutoff, so this is the way I'm doing it. Now the third thing are microwaves. These are about 1 meter to about 1 centimeter wavelength. Produced by electron tubes. If you ever taken a microwave apart, you'll see the electron tube looks like a weird light bulb. That's what it is. And we can cook food, but we also use microwaves for communications. You ever made a long distance phone call, it's gone through a microwave communications tower. Now, those are microwaves. They're about the size, somewhere around the size of humans. Now, a fourth thing, infrared. Beyond red. These are about 1 centimeter to about 1 micrometer, 10 to the minus 6 of a meter. Produced by motion of particles. In an object. So these have all sorts of uses. Keep food and animals. You ever been to a ever been to a restaurant or buffet where the food is under a funny light? That's an infrared heater keeping it warm. They also use those infrared heaters in feedlots to keep the animals warm in winter. And of course, IR goggles. You ever watched any of the any movie where they use see in the dark technology? That's infrared goggles. Fun to play with. Now, a few other wavelengths you have to worry about. Now, after infrared comes visible. Now, visible. And what is the acronym for visible? Red, orange, yellow, green, blue, indigo, and that's the same. Indigo and violet. Actually, we should just call it purple. However, more of a purple, dark purple. Indigo violet. Sir Isaac Newton, when he broke white light up into the visible spectrum, decided there were 7 colors because 7 was a magical or holy number, so he had to have 7 colors, so he split purple up into indigo and violet just to confuse things. So, red has longest wavelength, lowest frequency, which means it has the lowest energy. Now, violet, the shortest wavelength, highest frequency. So that means it has the most energy. Regardless, we're looking here something around 1,000 nanometers in wavelength. Now, to be more specific, if we look at the green sheet, you'll see cutoffs for the various colors. Now you notice on this one, American, they go blue, violet. They don't have indigo and violet. So they have violet or purple. I prefer purple to violet. Anyway, so you see the cutoffs there. Now be careful. On the diploma, they don't ask for exact cutoffs like that. And once again, we are going to argue. Is the cutoff for red 3.84 times 10 to the 14? It's frequency. Sorry. Hertz? Is that yes or no? It's somewhere around there. Here we're getting into an argument regarding colors, and I don't want to go there because I don't want to. So the frequency and wavelength, that gets interesting just remember it's something around 1,000 nanometers. Actually, it's about 650 to about 340 nanometers. But once again, the textbook, page 638, talks about this nicely. Okay, so as I was saying, it's about 650 to 340 nanometers. Yes, something you should remember. Okay, now next, sixth one I want to talk about is ultraviolet, or beyond the violet. Now this is about 100 nanometers to about 10 nanometers in length. This UV light is tanning bed. And the sun. This produces tanning as skin damage, skin cancer. Oh, and vitamin D. So you do need some of it, but too much of it gives you skin tanning and skin cancer. Oh, this is produced by valence electrons jumping down. Down in energy levels. Think back to chemistry, valence electrons. We will be talking more about this later. That's ultraviolet. We go here. We're getting down roughly protozoa, single-celled animals down to molecules. Now, after ultraviolet is X-rays. Now these are about 10 nanometers to about 1 nanometer. And I want you to note 1 nanometer. Oh, sorry, not 1 nanometer, 0.1 nanometers, sorry. Now, as an aside, an unofficial is an angstrom. Sorry, 1 times 10 to the minus 10 meter is sometimes...
Leah Noel to the office, please. So Leah Noel.
1 times 10 to the minus 10 meter is sometimes referred to as an angstrom. That's an A with a little circle above it. It's not an official SI unit, but you might see it written in books or notes somewhere. So be careful about that. Now, X-rays. Now these can penetrate less dense materials. Like flesh. But are stopped by more dense materials. Like bone. Now,
Nicola Simino to the office, please. Nicola Simino to the office.
so these are produced by sudden deceleration, CLE, of electrons. And I can vaguely remember when I was a little boy going to the shoe store, they had the X-ray machine in there, so you could X-ray your feet in the shoes and see if they fit. It was a gimmick. Probably gave you cancer, but anyway. So here we're dealing with X-rays, getting down to the size of atoms. Now beyond that, gamma rays. So 9 now gamma rays, these are 1 angstrom to 1 times 10 to the minus 5 of an angstrom, or 0.1 nanometers to 0.01. It comes after nano, and then pico. So sometimes the angstrom is an easier unit to use. Now, these are used in radiation therapy. Therapy to treat cancer. Actually, gamma rays are quite dangerous, quite toxic. They kill cells. They kill fast-growing cells, like cancer, faster than they kill regular healthy cells. So you're poisoning yourself with gamma rays or radiation therapy, but hopefully you're killing the cancer cells faster than you kill yourself. Now, these are formed in nuclear reactions. Or decay. Last but not least, you notice here on the pink sheet stops at gamma rays. If we go to the green sheet, we've got X-rays, gamma rays overlapping. They got dash, dash, dash here. Some people talk about cosmic rays. I'm putting it in because I can. These are even smaller. 1 times 10 to the minus 5 angstroms. Or 0.01 picometers and smaller. These are very dangerous. They can actually break atoms apart. These are created when high energy particles from outside the Earth or from the cosmos hit Earth's atmosphere. These rays come from the cosmos, hence cosmic. Very, very dangerous. Fortunately, the Earth's atmosphere does a good job of filtering them out. Now, that's it for EMR. Read through the notes. Watch the videos again if you need. Take notes if you need. Get ready to do the questions next class. Have a good weekend.